Now I'm happy to welcome Jay and Isaac to the stage from Uber. They are very big users in general, and they will present one of their use cases to us today. So take it away, guys.
Hello, everyone. Thank you for coming. My name is Jay Bae. So we are from Uber to talk about powering Uber Marketplace's real-time data needs with Elasticsearch. So this is a visualization of the number of trips which were made in New Year's Eve 2017. The size of the hexagon is showing the number of trips. As you can see, this animation, the Uber Marketplace has a supply and demand. Interaction between them is creating trips and fare. So it's really important to have a powerful analytics technology to make the Uber Marketplace more efficient and to find out how we can get better in the future. One of the most typical analytic questions in Marketplace is how many Uber access were open in San Francisco in the past 10 minutes in financial district. How many is the count? So metric, what we want to have. Uber X, the vehicle type, open vehicle status, San Francisco financial district is a geolocational dimension, past 10 minutes time dimension. So basically, we want to retrieve and aggregate the various metrics under the combination of the dimensions. So with the power of analytics, what kind of a business problem we can solve? So one of the most important business problems is dynamic pricing. Dynamic pricing can adjust your fares based on imbalance of supply and demand. So we need to aggregate in a real time, supply metric and demand metric to find out what kind of a balance are there across the different time ranges under the different granularities in a real time.
Obviously, knowing the current and previous status of Uber's marketplace is important for providing useful and informative recommendations and guidance. We also want to take these recommendations and feed them back into the system and check how well they're doing to make sure we're providing the best recommendations possible. Another use case I want to talk about is with marketplace health. Broadly, marketplace health is looking at the overall efficiency and experience of the Uber marketplace. So marketplace health encompasses a number of different types of metrics that they might want to look at. These could be factors going into algorithms that run at Uber, like for dynamic pricing or others. And it could also look at other parts of the marketplace experience, like how many trips were requested, how many trips were completed, the ratio of things like these, as well as ratios of estimates versus actual time. In addition to having these metrics, we also want to look at them across a number of different dimensions. So we might want to check the health of the marketplace in the last few minutes, but we also might want to check the health of the marketplace a few weeks ago, a few months ago, and across these different time ranges. Similarly, not only do we want to look at the marketplace on a city-wide scale, but we might want to drill down into some specific subsection or neighborhood of a city. Another use case we want to enable is data science. Data scientists have, of course, a diverse set of requirements of different metrics, different ranges, and different types of data that they can require from our system. So I'd like to hand it back to Jay to talk about some of the challenges of implementing an analytics system.
First of all, Uber Marketplace data's model is quite complicated. The single business event cannot be mapped to the single metric easily. For example, if you open the app, your status will start as a looking, and then if you click the button to request a car, and Uber Marketplace core service will try to find a car in the nearby and pick up those one car and send a dispatch request. And the partner accepts the dispatch request, and then the trip status on the partner side will be changed to en route, and the rider's side, the state will be changed to waiting for pickup. And car arrives to pick up the rider, and partner swipes the app to start a trip, and both sides, the state will be changed in the on trip. And after a while, trip state will be changed and completed. So with the various metrics to have, so for example, if you want to time difference between each state, so without supporting on the complex data model, entire event should keep the entire history of two entities. So it's not easy to make those events every time in the system. So we need to have a complex data model. So another challenge is fine-grained geotemporal. As you can see, there are so many hexagons in the San Francisco Bay Area, more than 10,000. Why Uber is using hexagon instead of existing geohashing technique, including like a quad tree-based one or Google S2 parallelogram? One of the major motivation is rectangular-based geohashing technique has two classes of neighbors, horizontal and vertical, and diagonal. But if we use the hexagon, we can always have a single class of a neighbor, something like a circle-like a shape. And also another benefit is circle-like a shape guarantee that we can have like a smoothing effect from the high density center area, and as going through the outer surface, we can have a smoothing effect. So even though we decide to take the mini granularity, which is already coarse, there are 1,440 minutes in a day. Another one is combinatorial explosion of a dimension. So there are several multiple vehicle types and many cities, many hexagons, and there are many vehicle status. If we multiply everything to get an entire number of a combination of a dimensions, its number will be really huge. So besides of those technical requirements, technical challenges, which features should be required in the data analytics system? First of all, queries should be flexible as a Boolean filter. This is a snippet of our internal query language for Elasticsearch. This can be interpreted as a Boolean filter in Elasticsearch with the in operator and equal operator. So queries should be flexible to cover arbitrary combination of multiple dimensions. So another one is we need to have various aggregation features. Group by, which is a terms aggregation, and many aggregation feature, metric aggregation such as sum, average, top band, or histogram. So time series analysis is really critically important. So we should be able to look back from the past to see how metrics are being changed as time goes by under the specific combination of a dimension and some geolocation. So in terms of ingestion, such as a data pipeline integration, so we need to have a low latency from end to end. Ingestion should be done within a few seconds to implement the real-time analytics. As I mentioned earlier in dynamic pricing doesn't care about the past. We only care about what's going on right now. So we need to have a low latency of data ingestion. The data model. So as you can see, the previous slide, the complicated data model. So single document, a single metric cannot fulfill every requirement of Uber Marketplace analytics. So we need to have an entity model with the idempotent, and we will have a huge benefit if the storage system can support joint operation also. The last but not least, the system should be scalable as a linear fashion. The data retention, because the system cannot have a data forever, so we should be able to remove the outdated data, so which means time to live. And also monitoring can be done easily, and to extend the system, its operability should be easily done to integrate the legacy system. So in a single phrase, the solution we are looking for is multi-dimensional geotemporal real-time analytics. How we can implement with the existing open source solution, like a key value stores, Cassandra. Cassandra can guarantee the scalability and high availability without compromising performance. But to implement the analytic system with the Cassandra, a lot of things should be hacked, including to implement the data to delete the outdated data, compaction strategy should be tuned. And to implement the data model, lightweight transaction can be used, but which is quite limited in Cassandra. And Cassandra has allow filtering and in operator, but it cannot be compared to flexible query DSL in Elasticsearch. And for batching mutation, Cassandra has a few confusing concepts such as logged, unlogged, and coordinator node. but Elasticsearch bulk API is pretty straightforward and performance is awesome. Yeah, let's talk about Druid. Druid is a pure metric aggregation engine with the high performance column-oriented distributed data store. So it has a lot of advantages such as native time series support with the data rollup. To implement the time series in Elasticsearch, we need to manually generate the index name with the timestamp format string, but Druid can do it on their own. So if ingestion query performance is very good, so in some cases, which is much better than Elasticsearch, and also it can support independent batch indexing through Hadoop. And if we create an index data in the HDFS, Druid will take over with handover data from HDFS. But it has a few disadvantages. There are too many moving pieces. So due to these many moving pieces, Druid can show off. So it's a powerful distributed technology, but deployment operation is really tedious. And also Druid cannot support the data mutation. So strict immutability will require complex stream processing. So what about the Elasticsearch? Elasticsearch, distributed, RESTful, search and analytics, right? So Elasticsearch is a document storage. It's a double-edged sword. So because it's a document storage and it supports a mutable data model, which is really killing feature, we can have an idempotent because we can store only once document under the same document UUID. So uniqueness exactly once will be supported automatically. So data pipeline will be much easier. So as we can put the multiple JSON partial document under the same document ID, the join operation can be implemented partially. But the problem is everything in Elasticsearch is a document. So in terms of aggregation execution, the entire rejected set should be linearly scanned, and aggregation buckets should be created on the fly, so it can cause performance and scalability issue on larger scale aggregation. So memory pressure, disk I/O pressure. So even with those disadvantages, why we decide to use Elasticsearch? Because Elasticsearch can fully implement the complicated data model in Uber Marketplace. For example, we have two different events stream, trip requested and trip completed. Usually Uber trip will start in the pickup location and the pickup time, and it will be completed in the drop-off location and drop-off time. So we have two different event streams, but how can we calculate the completed and requested ratio? This metric is really important because if this ratio is less than 100%, we are losing potential trips. So if the storage engine cannot support join operation, we need to implement the join in the ETL stream processing or query layer. So what if the stream processing should merge then? So when the requested happens in the ETL side, and it needs to keep the long hour window and to merge the completed. But the problem is that sometimes trip can take longer than expected. Then managing really long window in the stream processing is quite really hard. And the query side joining, so we can send the two queries separately in the requested data source and completed data source, so we can join based on trip UUID. But the problem is geolocation dimension and time locations are totally different between two data streams. So how we can generate the query? It's not an easy problem. So if the Elasticsearch can support the entity model, we can join on the same trip ID on the requested and completed. So when the requested happens and arrives into the Elasticsearch, we can generate the trip document with the trip ID, and later completed happens and completed events arrive to Elasticsearch. We can put completed information under the same document, trip document. That means we can mark the flag completed as true using offset operation in Elasticsearch. Then we can get how many numbers of trips were completed or not completed. So we set up the architecture of Elasticsearch. It's pretty simple. This is common example of a Lambda architecture with the batch ingestion and the real-time ingestion. So marketplace services are publishing messages to Kafka. And there's another set of the data pipeline from Kafka to HDFS. So we are using Samza as a Kafka consumer, and Samza are publishing message to Elasticsearch with the multiple steps of pre-processing. And whenever we want to backfill the historical data, we can run Spark job from HDFS to Elasticsearch. And we have an additional storage manager for data source metadata management and monitoring of an Elasticsearch cluster, and additional operation management. And we have a separate query layer. So speaking with the data pipeline, I mentioned earlier that we are using Samza for Kafka consumer. At the time, Samza didn't support Elasticsearch producing, so we made on our own bulk indexing client with the borrowing REST client class from Elasticsearch Hadoop connector. So definitely we are using Spark Elasticsearch for Spark ETL, and we configured to ignore a few exceptions to have a flexible ETL data pipeline. For example, we want to update existing trips, but it's not easy to find out which trips existed in advance. In that case, we don't care about non-existing trips even with the update. But without configuring these exceptions, the entire data pipeline will be halt because of document the missing exception. So to avoid those kind of uncomfortable situation, we configured Spark Elasticsearch connector to a few exceptions.
So let's talk a little bit more about how we're deploying Elasticsearch. You saw in that high-level architecture diagram that we're using Lambda architecture and Samza and Spark in order to write into this box called Elasticsearch. But the reality is we don't have just one thing called Elasticsearch. We actually have a few different clusters that are running. So separating out our data into a few different clusters has a number of advantages that it gives us. One of the biggest advantages is that we're able to separate out different data sources, different query users, and so on by differing SLAs or reliability guarantees. For example, we might have some cluster that has no backfill jobs because it doesn't want to be exposed to the stresses or the queries related to backfill jobs. We might have another cluster that has a second copy of a data source because it needs to have a different set of guarantees than another user. In order to query these multiple clusters, we decided to implement our own query layer. Elasticsearch has some support for this type of situation using tribe nodes, but we didn't feel tribe nodes were the best solution here. Tribe nodes introduce a number of challenges, such as the number of connections from that tribe node to the nodes in your cluster, as well as issues such as the index namespace issue, where index names can collide across clusters, which can also be a difficulty. We decided instead to implement our own query layer that sits on top of Elasticsearch, which accepts our own types of queries and routes them appropriately, and also does a few other things that we'll talk about. So we have our own query layer, which is deciding which Elasticsearch cluster to execute a query on. We have a few different pieces of metadata that are associated to one of these data sources in our system. And here's an example of a few different fields that we might provide to our system. Information we want to provide to it includes things like which clusters a data source is available in, as well as information about how it's retained in those different clusters, how it's routed in different clusters, and so on. Another thing that our query layer provides for us is the ability to accept queries in our own query language rather than the Elasticsearch query DSL. One of the difficulties with the Elasticsearch query DSL is kind of a double-edged sword of Elasticsearch. It's very expressive. I have here a fairly simple requirement, or a very common requirement that we get of grouping by two fields, which translates to a terms aggregation nested within a terms aggregation, so group by A and then B. I think I counted this out correctly, and it winds up having 5 end curly braces at the end of this single line of JSON, which gets to be kind of excessive. We implemented our own query language to provide the the simple features that our users are commonly requesting, and then as we need, bring in part of the more expressive parts of the Elasticsearch query language, again, on a as we need them basis. Another thing that our query layer is able to help us with is in ensuring the safety of queries that we're executing. If you've worked with aggregations a lot, you may be familiar with some of the cases that you kind of need to avoid, like terms aggregations that are nested within terms aggregations and so on. In bad cases, this can eventually lead to really bad GC pressures or even out-of-memory errors happening in your cluster. Unfortunately, Elasticsearch will accept queries like give me a terms aggregation of every single globally unique identifier in an index, something like that. And obviously that's not going to work out. We have a few different ways that we try to address this issue. One is by estimating the cost of executing a query before actually executing it. There are a few different ways we can do this. One of these is for some fields, for example, like a status identifier or certain types of identifiers within our marketplace services, we can estimate out the cardinality of actually using this field ahead of time in order to estimate the cost of running the query. Another, of course, important thing we can do is enforce some sane limits. So a user can't execute a terms aggregation with size 5 million, for example, or something sufficiently high is not going to be accepted. Here's again an example of some metadata that we might attach to some fields within an Elasticsearch data source. These could have, for example, the estimated cost of grouping by that field, as well as maybe some filters that need to be used in order to make this field really useful to a user. Another issue that our query layer helps us to avoid is problems with scripting. Painless in Elasticsearch 5 tries to address some of these issues, like the while true problem. But for those who are using Groovy or other scripting environments, this is more of a concern and makes it a lot less safe to use scripting. We still want to have this expressibility of the Elasticsearch queries, but of course we don't want users to execute something like this, which will cause, it will cause problems on the node that winds up executing it. Our solution is fairly simple to provide a safer set of scripts that cover most users' use cases, but don't allow them to express this type of problematic script. We mentioned before that we have this storage manager that sits outside of Elasticsearch and does some management and retention type tasks. At the time, Elasticsearch Curator didn't meet our requirements. I believe it was because of cascading retention rules not being available. So as a result, we added some of our own code to manage these index retentions. We had one kind of interesting learning from this, which revolved around the date format string that we used on making our indexes. We used a format string like this one at the bottom with year, month, and week. But unfortunately, this has kind of an interesting edge case where it's possible to get an index name with something like the 52nd week of January 2017, which doesn't really make a whole lot of sense. It doesn't make a whole lot of sense to humans, and unfortunately it also doesn't make a whole lot of sense to the JOTA library either. The problem here is that the week numbering is aligned with the week year and not with the Gregorian calendar year, which we're using here in the YYY format. The solution is to use the correct date format string, which is with the XX format specifier, and of course, when making these format strings, be a little bit more careful about how you generate them, since the libraries that you're using may not always clearly complain if you're doing something that doesn't exactly line up all the time. Monitoring is another area where we deployed some of our own code. Elasticsearch has some great tooling around retrieving metrics from it, loading those, again, back into Elasticsearch and doing monitoring and alerting on that. But at Uber, we already have an observability and monitoring systems in place, so we wanted to prioritize working within that ecosystem. As a result, we wrote some code that periodically pulls Elasticsearch metrics and ingests them into Uber's monitoring system. And that way we're able to get graphs, alerts, monitoring, and all the other features that we'd want. We had a bit of an adventure troubleshooting one issue with monitoring, though I'd like to walk through. The issue that we observed was that ingestion latency, so latency from the ETL job to actually load data into Elasticsearch, went up. And we couldn't immediately find a reason why. We looked at the usual suspects. We looked at GC time, disk utilization, indexing time, network utilization, and so on. And we didn't find something in the Elasticsearch metrics that really pointed to a cause. Eventually, we found the issue, and the issue was that the time for communicating between two nodes in the Elasticsearch cluster was slowing down. So to give a little bit of context of what happens when a bulk request is received in Elasticsearch, Elasticsearch looks at the individual requests within that bulk request and sorts them by what shard and index they're going to. So it takes all of the requests that are going to shard 1 on index A and puts those in one group, and does the same for shard 2 on index A, and so on for all of the requests that are in your bulk indexing request. And then it forwards those requests, the request that's only for shard 1 on index A, to the node that holds the primary replica for that shard. And that was unfortunately the part that was slowing down. It was taking a bit longer for Elasticsearch to talk to the specific node that was holding that shard. Unfortunately, in our case, this wasn't long enough for that node to actually lose membership in the cluster. It was just long enough to show up in the ETL job that something was not quite right. Elasticsearch doesn't directly tell you what the latencies between different nodes in the clusters are. So we had to diagnose this by inserting some code into Elasticsearch that tells us what these specific latencies were, because these metrics were not emitted as is by Elasticsearch. More broadly, I think the lesson here is also to avoid operations that can wait on a large number of nodes or a large number of network connections, since that kind of increases the probability, I think, of this type of issue happening. And to kind of wrap up this story, once we identified the specific nodes that were having an issue, we were able to very quickly diagnose where that issue was and find a misbehaving piece of network equipment and repair that.
Additional lesson learned. So first of additional lessons learned was how to deal with the imperfect circuit breaker. Elasticsearch contains multiple circuit breakers to prevent operations from causing an out-of-memory error. But even with the nice circuit breaker, we haven't seen a lot of times client nodes are going down under heavy aggregation queries. So it has a really long GC pause in the worst case. It was killed because of out-of-memory. But somewhat, data nodes were totally safe. It didn't trigger any circuit breaker either. The situation was we have many shards, which is large fan-out. So this is an example of a query, heavy aggregation queries. The grouping by terms aggregation of a hexagon ID. As you can see, this, as you saw in the previous slide, it has really high cardinality and status. So date histogram aggregation has only single day, but interval, the granularity is 1 minute is quite short. So potentially it can create more than 1 million aggregation bucket, 24 hours, 6 minutes, 10,000 hexagon, and 10 statuses. So what we tried, so recently aggregation bucket overhead was implemented in the Elasticsearch latest version. So we suspected this might be helpful. So aggregation bucket overhead will be counted when aggregator object is being created, and that amount of memory will be released on the aggregator.close method. But it wasn't helpful because the client nodes didn't go through this execution path. And then, was it caused by in-flight request circuit breaker? So in-flight request circuit breaker is recording entire size of the allocated memory to receive the request, and then it released the memory on the transport channel .close method. But it was not helpful because the problem was not request payload size. The problem was response. So client node is trying to reduce entire partial result from all shards, but while reducing those data, if the partial data is really huge, it can try to allocate excessive amount of the memory, which can boom Elasticsearch client node. The solution is how to make response size smaller. First solution is we need to reduce the fan-out size as smaller as possible with the custom routing. So in the previous diagram, there was an 8 fan-out, but under the custom routing, we can reduce it to the single shard. So with the small fan-out, the more common parts will be reduced in the data nodes in advance. So overall response size will be smaller. But the problem of custom routing is skewed data routing is risky because it can create a hotspot. Also, it can put more pressure on the data nodes, so it will be more likely to trigger circuit breaker, which means we will lose more queries. So another solution is we can split the query into multiple sub-queries with a small time range. For example, daytime histogram for 1 month can be split into 3 sub-queries with the 10 days. But it's really hard to set up optimal boundary. Something like 1 month should be okay, or 1 week should be okay, or 3 days should be okay. It's really hard to find out the optimal boundary in advance. So initially we took this approach, but we decided not to take this approach was it has additional latency because it will repeat the same execution multiple times. So we have seen many times the timeout issue in the front-end side. So our solution is we can implement in-flight response circuit breaker. So this is already open issue in GitHub. So we can record allocated amount of the memory for the single query in the response handler. So ideally, circuit breaker should keep all amounts of the memory in flight through Elasticsearch, but I didn't find the concrete interface to record on the starting point of a merging response and the finishing of the merging response. So I decided to take the approach of recording the number of amount of the allocated memory to handle single request. So it cannot track entire in-flight response memory size, but intermittent malicious queries can be totally prevented. So we haven't seen any client node outage since I applied dispatch into our Elasticsearch cluster.
So I'd like finally to talk a little bit about some newer features and upcoming features in Elasticsearch which are of interest here. One of them is similar to what Jay was talking about for executing larger queries is aggregation and partitioning so that terms aggregations or other aggregations can be partially computed. This does have some of the same limitations as what Jay was mentioning about queries taking longer, needing to be executed multiple times, but this does have the advantage of making it possible to execute queries in a safer manner with less risk of bringing down or causing undue pressure to an Elasticsearch node. Another feature I want to call out is query profiling, which we haven't had as much opportunity to use, but are excited to get started on. And then finally, a feature which isn't yet in a released version of Elasticsearch, but has been merged to master, which is this feature for partitioning indexes. So normally the way that routing works in Elasticsearch is you provide a routing field, and all documents with the same value of this field will be routed to the same shard in Elasticsearch. This does unfortunately have some limitations. There's, for example, this hotspot issue. If the distribution of these keys is not is skewed significantly, some data nodes could have significantly more pressure than others, and this can lead to more problems. What this change will enable is routing that same value, spreading it across several different shards of the cluster. So for example, you could have a routing key that's spread to 3 out of 10 shards in your index. There are workarounds that you can employ to get around this, but obviously once it's in Elasticsearch in a released version, it'll be a lot easier to use, and it'll be very helpful, I think, for scaling larger indexes.
Thank you for listening.
Okay, thanks a lot. We have like 8 minutes or so for questions. If we do not get to your question, the speakers will walk over to the AMA booth afterwards, like all the others, and answer more questions there. And if you leave, please don't forget to vote, since we always want to get more feedback. First question.
Hi. So my question was around how do you tackle like the dangerous queries, like the wildcard search queries, and what you suggested was figure out the cardinality to prevent those kind of. How do you find out cardinality, and then does that reduce your overall query execution if you're doing that kind of check for every query?
Sorry, could you repeat the last part of that? Sorry, could you repeat the last part of that question?
Oh, the last part of the question was how do you do that kind of a check? Like, are you using some Elasticsearch feature to calculate the cardinality ahead of time before making a dangerous query? And does that slow down your overall performance, making that extra check every time?
So the question was, how do we estimate the cardinality of fields, and how do we do that in a performant way? For cardinality, for some fields like statuses, for example, we know what the cardinality we would expect for these fields is. For other fields, we can take reasonable upper bound estimates of what they'll be. So we'll know that, for example, how many spatial units, for example, we expect there to be in a city. And that way we don't have to incur a lot of cost of running additional queries to actually estimate the cardinality.
Hi. I was wondering, you were talking about having documents being combined together based on trip ID. I was wondering, did you guys use the parent-child relationship for that, or did you do it in a different way?
Hey, we don't use the parent-child relationship and parent-child aggregation. The first of all is with the simple join operation under the same trip UUID, we can implement everything we want. And the second one is we haven't tried yet, but parent-child has additional overhead in Elasticsearch about the data partitioning, and parent-child aggregation has some performance issue, so we haven't tried it.
I was not actually. How did you measure the node-to-node latency of, like you showed in the graph, like 30 seconds, 40 seconds? How did you exactly measure that?
I didn't quite catch that. I think it was about the latencies that we were showing.
So you were showing the node-to-node latency of 30 seconds, right? I think you didn't expect that. So how did you measure that?
So the node-to-node latency part?
Yeah.
Yeah. So for that part, Elasticsearch did not emit those metrics out of the box. We had to add some additional code into Elasticsearch to emit that, to instrument that.
Thank you.
Hi. Could you please explain the rationale for using SAMZA for streaming? And could you compare with other technologies like Storm, Spark, Flink? Did you evaluate? What is your thoughts on it?
I joined Uber around 2015. At that time, Spark streaming was not stable because embedded Kafka consumer in Spark streaming was still using high-level Kafka consumer, which has a heavy dependency on the zookeeper side. So that's why we didn't decide to use a Spark streaming. But Storm, Uber, before I joined Uber, Uber was using Storm in the stream processing, but they saw a few technical difficulties on using Storm. So the Samza, and we compared the Samza, Storm, and Spark streaming, and in terms of stability and at least once guaranteed and stableness of a Kafka consumer, so Samza satisfied all our requirements. That's why we decided to use the Samza.
Did you get a chance to evaluate Flink, Apache Flink?
Marketplace team, the different section of a marketplace team is also using Flink, but we build up entire our platform, data processing platform using Samza. So especially our team is not using Flink, but different section of the Uber is using Flink.
More questions? Anybody? No? Okay. They're available for private questions over at the AMA booth. Thanks a lot for the talk.